Hello everyone. In this video, I will briefly explain the recent IV reuse attacks on Samsung Galaxy mobile phones like S9, S10, S20 and S21. But before explaining how the attacks work, I need to briefly mention what the authenticated encryption is and how it is used in these phones. So let me give a brief definition. The message authentication codes provide us the integrity of a message, and encryption provides a confidentiality. So if you can combine both of these operations, you actually get an authenticated encryption. So message authentication code is computed as a result of a complete pass over the data. If we provide both encryption and authentication, then we may require sometimes two passes over the data, but currently we have algorithms that actually can perform this only passing over the data once. So we can combine these two operations to provide authenticated encryption. So the picture is as follows. We have an encryption algorithm. In a normal encryption algorithm, we only provide plaintext and the key and obtain the ciphertext. But in authenticated encryption, we have more inputs like nonce, which should be only used once for every communication. And sometimes we may have associated data, which is a data that is not going to be encrypted, but still it will be authenticated. So actually the main idea here is that the nonce means that you have to use it only once. Okay, so it is a random value that is only used once, and actually the attacks that we are going to talk about reuse this nonce and this way obtains the secret key. So in an authenticated encryption, when we have these inputs, the output is the ciphertext and also a tag. This tag actually allows us to check the authentication. So this is the main idea. So far we had the authenticated encryption competition, which is shortened as CESAR competition. This competition started in 2013, and from these web pages, actually you can see how it proceeded. And at the end of 2017, the final portfolio of this authenticated encryption competition is announced. So the winners of this CESAR competition is as follows: Acorn, Aegis, Ascon, Colm, Deoxys 2, Morris, and OCB. But these algorithms are announced for different use cases, like cases 1, 2, and 3. And these are defined as lightweight applications, high performance, and defense in depth. So when the TLS 1.3 was in progress, I was expecting them to choose one of the winners as a authenticated encryption algorithm in TLS 1.3. But for some reason, they decided not to do it, but instead they use AES GCM and also Chacha with poly algorithm to obtain authenticated encryption. Another authenticated encryption algorithm is organized by NIST, but actually this competition is about lightweight cryptography, but the provided encryption algorithm should also have authentication. So this is why we have a lightweight authenticated encryption algorithm that actually started around 2016. So the submission requirements announced in 2018, and so the actual competition or the candidates actually applied for the competition around 2019, and currently 10 finalists are announced in March 2021. So we are expecting to have a winner or winners in the following 1 or 2 years. So aside from that, we have, as I mentioned, the GCM mode, Galois Counter Mode. So this is actually a counter mode. So we have counters, we encrypt counters with the secret key, and the result is XORed with the plaintext blocks. So if you have n blocks, you have n counters, and generally you increment counters one by one and obtain the key stream here, then XOR it with the plaintext to obtain ciphertext. But moreover, we have other parts where we have Galois multiplication operation here, which actually provides the tag. This way we obtain the authentication. But the important thing is that if you use the counter again here for a different encryption, for a different plaintext, the key stream will be here will be the same. So this is always warned, because in this mode of operation, the block cipher acts like a stream cipher, and in stream ciphers, if you put the same input, then you obtain always the same output as the key stream. So since the invention of stream ciphers, we know that the same counter or the IV or the nodes cannot be used twice. But this is actually what happens in the recent attacks that we have seen, that is published at ePrint Archive. So this is a work by Shakevsky, Ronen, and Wood. The paper titled "Trust Dies in Darkness, Shedding Light on Samsung's TrustZone Keymaster Design." So let me briefly explain what this attack is all about. ARM-based Android smartphones rely on the TrustZone hardware support for a trusted execution environment to implement security-sensitive functions. So this TEE runs a separate, isolated TrustZone operating system in parallel to Android. So we can divide into a normal world and the secure world. So we don't have access to the secure world. The secret keys are produced there, but we don't have direct access to these secret keys. So in applications, whenever encryption is needed, a secret key in the hardware side is produced, and then it's sent to the normal world in a modified version. So we only see that modified version, but we cannot go back to the original secret key. So this is how actually the mobile phones work. So even if you capture a device, even if you have access to the normal world, you shouldn't be able to obtain secret keys that are generated in the hardware side of this part of the world. So the implementation of the cryptographic functions within this part is left to the device vendors, who create proprietary undocumented designs. So in this work, authors actually cryptographic design and implementation of Android's hardware-backed key store in Samsung Galaxy S8, S9, S10, S20 and S21 flagship devices are reverse engineered. So actually, this is the main contribution of this paper. This is actually the hard part, but they achieved this. So using the same IV in a stream cipher produces the same key stream, which should be avoided, but this fact is known for decades. But still, in this work, authors observed that same IV is allowed to be used. So authors provided an IV reuse attack on ISGCM that allows an attacker to extract hardware-protected key material, and the downgrade attack that makes even the latest Samsung devices vulnerable to the IV reuse attack. So this way, they were able to recover securely generated AES, RSA, and even elliptic curve digital signature algorithm keys from encrypted blobs. So in order to simply explain how it works, in the hardware part of these phones, there is a 256-bit AES key called root encryption key. And using this key, actually 256-bit hardware-derived keys are derived. And this HDKs are obtained from this root key, but also a specific salt value that depends on the blob. But the problem is that this specific salt value generally generated from the data obtained from the user, for instance, application ID or that kind of known data. So the salt in version 15, which is actually used in Samsung S8, and version 20-S9, which is used in Samsung S9 phones, only depends on the application ID, which is set by the normal world. So if the salt value is fixed, since the root key is also fixed, so you give the AES GCM mode same counter and encrypt it with this unknown key, you produce the same key stream. So if we look at how it works, a hardware protected key K is encrypted via an IV and HDK using ASGCM to generate key blob B as follows. So this is the hardware generated secret key, we don't know it. And in order to encrypt it, the hardware side uses AES GSM encryption using the hardware defined key and IV. So the XOR is resulted as a blob, and this blob is sent to the normal world. So this means that for a given application, all key blobs will be encrypted using the same key, since the IV is the same. As the blobs are encrypted in IS-GCM mode of operation, the security of the resulting encryption scheme depends on its IV values never being reused. Key blobs are stored in the normal word file system, so they are accessible by an attacker. So, for instance, you want to capture a hardware protected key, KA, which we don't know, but we want to obtain it. So we only have the encrypted version of this key A. So we have BA obtained from this operation. So in order to capture KA from this BA, what the attackers do as follows. They import their own key, KB, by using the import key function. And they encrypt KB using the same HDK and IV. So IV reuse attack works here. They use the AES-GCM mode with the same counters. So this way they obtain the blob BB. So if you XOR 3 of them, what you obtain is as follows, because BA is actually the XOR of key A with this AES encryption. And BB is also KB XORed with the same thing. And finally, we have the third XOR operation, KB. So since we use the same IV and same HDK, these cancel each other. You end up with KA, XOR KB, and XOR KB. KBs also cancel each other since XOR operation is just addition modulo 2. So you end up with K. So this way, actually, the authors of this paper obtain secret keys. But this only works in Samsung S9 phones. In Samsung S8, the system doesn't allow you to choose your IV. So this prevents you to attack Samsung S8, but the authors can attack Samsung S9. And it is written here, Samsung S8 is not vulnerable since IV cannot be chosen by the user, but all key blobs created on the Galaxy S9 are vulnerable. So they announced it to Samsung and they updated. But then they realized that this attack does not work on Samsung S10, 20, and 21 because these devices use a different version, version 20 S10. And in this version, all key blobs are somewhat randomized because there is a salt value that is based on 16-byte random value. So here, actually, you cannot choose the same IV here. But they also observed that these phones also have backward compatibility, so they support version 15. So in that version, since the salt values are not randomized, they create key blobs using this version, and they perform the same attack, the IV reuse attack. So they actually perform a downgrade and then do the same attack. So these attacks actually affect more than 100 million devices. So initially, the authors contact Samsung and inform them about this Galaxy S9 vulnerability. A few months later, Samsung assigns a CVE with high severity to the issue and released a patch that prevents malicious IV reuse by removing the option to add a custom IV from the API. But then authors observed that they can downgrade S10, S20, S21 and perform the similar attack. So they also contact Samsung, and in October 2021, Samsung assigns another CVE, again with high severity, to the downgrade attack and patch models that were sold with Android Pie or operating system or later, including S10, S20, S21. And in this patch, they completely removed the legacy key blob implementation. So here, as we already mentioned, as we have known for decades, using the same IV in a stream cipher produces the same key stream, which should be avoided, and everybody knows it. So in an implementation, you shouldn't be allowed to use the same IV. So the mistake here comes from there. But so since this is a basic attack that we have known, the main effort of this paper is not this attack, but it is the reverse engineering. Because since this implementation is not documented, authors have to perform huge amounts of effort to obtain this implementation. So since nobody had the time to analyze other designs, similar attacks might be applicable to other black box implementations. So these results motivate the need for an open and standard cryptographic design.